So, our aim of the experiment is study of operating characteristic of electromechanical overcurrent relay and plotting a graph between trip time versus clock setting multiplier. So here the apparatus required is power supply unit, or in other way we can call it as current injection unit, and electromechanical overcurrent relay unit. As you can see here, this is the whole setup. The top unit is the overcurrent relay unit and the bottom unit is the current injection unit. So the top unit, this black square or this unit is the electromechanical relay, and the whole unit having the relay and some terminals. And similarly the bottom unit having power supply or current injection unit, which is designed to give the current to the relay or any relay or anything. This is like a current source. So if we see how the overcurrent relay works, this electromechanical relay use the induction principle discovered by Galileo probably in the late 19th century. As you can see, general concept. Then the magnetic system in induction disk overcurrent relay is designed to detect overcurrent in the power system and operate with a determined time delay when certain overcurrent limit have been reached. So that means when there will be overcurrent or when there is a current more than the current setting of the relay, that is called as overcurrent, then the magnetic system inside the overcurrent relay will activate and it will generate something. Then relay will give a signal to circuit breaker to trip the circuit. So as you can see, there is a equation given, equation of torque. So we know in the electromechanical relay there is a disc. So that disc rotates. When the disc rotates, it moves from normal position to fault position. Now let's see how the disc rotates. So the relay primary winding generally is supplied from the power system CT. That means the primary winding of the relay. That means inside the relay there is two windings. So the primary winding is supplied directly from the CT output of the power system. So we know that overcurrent relay is not directly connected to the transmission line or directly to the power system because of higher current, but it is reduced. Rather, it is reduced to the limit of the relay, then the relay can operate that amount of higher current. So that's why the primary winding is supplied in the power system CT via plug bridge. That means it is also not directly connected. It is connected via plug bridge with the from CT, then plug bridge to the primary winding of the relay. So, and the plug bridge is nothing but as ESN. So if we see here, this is the CT. This is the general diagram. This is the CT. From the CT, it is connected to the relay primary winding through the plug bridge. So this is nothing but the plug bridge. So plug 1, plug 2, plug 3, like above bridges are there. We'll see in details what is the plug bridge and how to operate the bridges. So it is written usually 7 equally spaced tappings. So these tappings is nothing but the plug bridge. So these 7 equally spaced tappings or the operating bands or the bridges determine the relay sensitivity. That means how the relay sensitivity means there is a current relay sensitivity to how much current. That is nothing but relay sensitivity. Relay sensitivity means relay current sensitivity. Right? Relay sensitive to 2 ampere of current or 3 ampere of current. That determines what are the tappings we have used. when the primary winding is located on the upper electromagnet and the secondary winding has connection on the upper electromagnet that are energized from the primary winding. That means secondary winding is connected from the primary winding and primary winding is connected from the CT output of the power system. Once the upper and lower electromagnet are energized, they produce eddy current. So how they will get energized? When there will be current. Which current? When there is a fault current or any normal current, the relay get energized. And according to and then after that eddy current that are induced into the metal disc. So that means when that two primary winding and secondary winding is energized, they induce some eddy current on the metal disc and the flow through the flux path. This relationship of eddy current and fluxes creates torque proportional to the input current of the primary winding due to two flux paths being affected by negative. That means the primary winding generates some flux I1, as you can see here. The primary winding generates some flux I1, secondary winding generates some flux I2, and the angle between that two flux is signified into sin theta. And depending on the amplitude of phi1, phi2 and sin theta, the disc getting some torque to move. But whether disc will move on any torque or not, let's see how the disc will move. So in an overcurrent condition, the value of current will be reached. What happens? In overcurrent condition, the value of current will be reached that overcomes the control spring pressure on the spindle. So that means depending on the flux, torque generates, and if that torque overcomes the pressure of the spindle, then only the disc will rotate. And let's see the whole. So in overcurrent condition, a value of current will be reached that overcomes the control spring pressure on the spindle and the braking magnet, and a two things is there, pressure coil on the spindle and the braking magnet, then causing metal disc to rotate towards the fixed contact. Now understood how the disc will rotate. So that means when there will be a current, that means when there is a current, then the torque will generate. But when there will be a current more than the current setting of the relay, then what happens? The torque is more than the pressure on the spindle and the braking magnet. Then the disc will start to rotate. That means there always some torque generates. But when the torque is more than the pressure on the spindle and the braking magnet, then the disc rotates towards the fixed contact. This initial movement of the disc is also held up to typical positive value of current caught into side of the disc, and the time taken for rotation to make the contact is not only depend on the current but also the spindle backstop position. Now you understood how the disc rotates, but the time taken to move towards the fixed contact not only depends on the torque or not only depends on the fault current, it also depends on the position of the disc. That means the spindle backstop position. So we'll see which one is the spindle and here is the backstop position. So that position is known as the TSC. So generally electromechanical overcurrent relay is having TSN maximum up to 1. It can start from 0.05 to 1. This is the TSN of a electromechanical overcurrent relay. It cannot exceed more than 1 in case of electromechanical overcurrent relay. So you will see this diagram, you can understand how the relay operates. This one, the electromechanical overcurrent relay. So you can see this is the CT output is get connected to the relay unit and through a clock bridge. This clock bridge is nothing but the clock setting of a relay. Then depending on the current, it will generate some torque, the disc will rotate, then the spindle will touch the fixed contact of the relay. Then after that, so this coil will be energized, and after that this one will be short circuited, and that will be the trip signal for the circuit breaker. So generally we know in the circuit breaker there is missed trip signal, and that is NO or NC any type. That we will see in the power supply or the current injection unit where is the NO and C is there. So next, so which relay we are going to use here in this experiment? That is the CDG11AF relay. This is the standard relay manufactured by the Alstom, and it is having inverse trip time characteristic, and it don't need any auxiliary power supply. So it is self-powered auxiliary supply. It is self-powered. That means whatever the current you are giving, that is normal operating current, is the power supply for this electromechanical overcurrent relay. No extra power is required in this electromechanical overcurrent relay. And we are going to use this CDG11 model made by Alstom relay to test here in this experiment. And this relay, you can see here it is written, this relay is used for overcurrent and also used for arc fault relay. But we will see whether this CDG11 which we are having can we use for the overcurrent or arc fault or not. We will see in the next slide. So what are the relay specification we will see? That means specification of the relay which we are going to use, that is CDG11AF relay, overcurrent relay, electromechanical overcurrent. So what are the features? You can see identical time and current characteristic on all tappings. All tapping means, you can see, let me show you here, these are the tappings or these are the clock settings. So this is clock setting at 0.5, clock setting at 0.75, clock setting at 1, clock setting at 1.25, clock setting at 1.5, clock setting at 1.75, clock setting at 2. And right now, as for this image, clock setting is selected to 1.5. So these are the clock settings. And it tells at each clock setting, the characteristic is identical. So identical time and current characteristic on all taps. That means in which clock setting we will select or in which tapping we select, we will get identical time and current characteristic. And this is self-powered, no necessity for a separate auxiliary supply. That is the advantage of this relay. Then another is high torque and ensuring consistent timing even under adverse conditions. That means if there is some disturbance is also there, but still this relay will work. This is the advantage. Let's see the technical details of this relay, CDG11AF relay. As you know, made by the Alstom, and the current rating 1 ampere or 30 ampere it is means if this CDG11 relay is manufactured for 1 ampere rating as well as for 30 ampere rating. So we are having this 1 ampere rating. We will see in the nameplate of the relay what is the current rating is written. Next is IDMP setting. Let's see the image if you can understand how. So this is the relay, overcurrent relay. It will zoom this one, nameplate of the relay. As you can see, here it is written 60 secondary is 1 ampere. So that means here current rating 1 ampere or 30 ampere, we are having 1 ampere because 60 secondary rating is 1 ampere. Next, IDMP settings 50 to 200% in 7 equal step of 25%. So that means 50 to 200% of 7 equal steps. So 50 to 200% of what? 50 to 200% of the current rating. Understood? 50 to 200% of the current rating. So you can see here 0.5 to 2, that is 50 to 200% of the current rating. So current rating is 1 ampere. So 50% of 1 ampere is 0.5 and 200% of 1 ampere is 2. And in 25% increase like this. In each step 25%. So that means 0.5, 0.75, 1, 1.5. 1.25, 1.5, 1.5, like this we have 7 equal steps. We have 7. 1, 2, 3, 4, 5, 6, 7. Now starting current. Starting current is 102 to 105% of the current setting. That means current setting means that is the plug setting. So means right now here plug setting is 0.75. If we shift this to here, current setting will be 0.5, and here current setting is 1.5. So 103.3 to 105%. That means if let current setting is 1 ampere, 1.03 to 1.05 ampere. If your current is increasing, then the relay will start to operate. That is the starting current of the relay. Less than that, that is the normal operating current of the relay. Current not more than 1% of the current settings. Here important things, the operating time, that is 0 to 3 seconds or 3 seconds at 10 times. This is 10 times it is showing means 10 times of the current setting. So if you are giving 10 times of the current setting, then relay should trip in 3 seconds. So that is the characteristic. We will see in the part 2 what are the different type of characteristic, what are the different type of inverse characteristic is there, that we will see in the part 2 of this video. For this relay which we are going to study here, we are having 3 seconds and 10 times at 10 times current setting. Here we can see in this, let me complete then I will come. Then the resetting time is the 9 seconds for 3 second relay. So this is the 3 second relay, because 3 seconds or 10 times relay and relay characteristic. That means this is the, we already know that this is the inverse characteristic relay. So inverse characteristic relay at 3 seconds means when 10 times operating current, we are getting 3 seconds. So characteristic we can name it as 3 second relay or 3 second characteristic. In detail we will study in the part 2, 3 second relay. So 9 seconds for the 3 second relay. So that means the CDG11AF is also manufactured for another type of inverse characteristic relay. For this relay which we are having right now, or which we are going to study right now, or which we are studying, is 3 second relay. And resetting time means once the fault happens, the disk should come to its home position and it will take 9 seconds. That means we should know this time, we should know this resetting time, so that if fault happens and within 9 seconds again fault happens, then whether relay will perform or not, depending on the situation, we will decide. Before that we should know what is the resetting time. Then next is thermal rating. The thermal rating means that is the how much current the relay can withstand. That means we know that the overcurrent relay, it takes the current. So as per the characteristic, in this characteristic, it will give some current. What happens? Okay, if it gives some current, relay trips. That means any current you will give, relay will trip. But just imagine, relay rating is given 1 ampere, relay will give 1000 ampere. The relay will trip, but what will happen to the relay? Why not to the relay is directly connected to the transistor? Why through the CT it is connected? So that means there is a limit. It's not like that we can give any current, relay will trip. So that signifies the thermal rating. So that means it tells that this relay is can 20 times the maximum current setting or the setting current for 3 seconds. So that means 20 times of the current setting. Current setting one I am calling that is the plot setting. So here you see this 0.75 or 0.5 or 1 is the current setting, and 1 ampere is the current rating. So current rating is the 60 secondary, current setting is the plot setting. That is the pickup current, nothing but the current setting. So here you can also see there 20 is retained maximum. That means if 20 times you are giving current, then the relay can withstand 3 second maximum. Above 3 seconds, what will happen? It will may damage. So that is the thermal rating we should consider when we will install the relay in the field. And as well, the relay application, this is used for the phase and earth fault protection, and in time gated system or estimation transformer period, etc. As we know, where the overcurrent relay is used. So let's see in details. So here we can see all these terminals have the clock settings. Right now it is selected to 0.7, and this is the table. This is the table or the corresponding PSM with respect to time table. So as you can see, we are having different values of PSM and we are having different values of time in second. So before that we should know what is the PSM. What is PSM? PSM, you know that it is the ratio of fault current upon clock setting. So this is the ratio of fault current what we are applying divided by clock setting for the PSM. That means if PSM is 2, it is telling that there the time will be 10. So what is this time? This time is nothing but the calibrated operating time. That means if PSM will be 2 and 10 is written to see at 10 operating time, at 10 second on the trip plane. That means we can predict what will be the trip plane for what will be the current before operating the relay. This type of things happens only in case of electromechanical current relay directly. So, and also I have told you that the relay operates on the disk. This is the disk. The disk moves, and the time taken the disk to moves from normal point to the fault point is not only depends on the current but also depends on the spindle position, nothing but the TSM or time setting multiplier or time multiplier setting, whatever you can. So here you see this is the disk, and this disk is attached with the spindle, and this spindle is attached with a knob. So the position of the spindle or this position of the knob, whether here this is circular motion, like here you can see this is the disk and this is the spindle. So this is the disk and this is the spindle. So the position of the disk spindle means what is the starting point of the spindle. If starting from here, it can start from here, it can start from here. So that starting point will gives you the TSM. So here right now it is starting from a point which is giving you the PSM. This is the PSM scale. So here this 0.7 is written, 0.6 is written, 0.5 is written. So right now it is pointing to 0.7. That means the PSM is 0.7. That means when the relay will start from the not from the starting point, it is starting from the somewhat ahead of this one. So which is telling you 0.7. So on 0.7 relay is moving towards this. So how to calculate right now the trip time? Before that, let's see if this spindle will moves, what will happen? This spindle will moves or the disk will move, what will happen? This spindle, it will touch with this arc. This is this arc. So what is there inside? Two terminals are there, and from the two terminals and from this moving contact, we are getting a signal of trip. So what type of signal we are getting? We are getting N over S. So as you can see from this diagram clearly that this moving part, this is the moving part, and this one fixed part. This moving part is connected or touched with this one. So this and this terminal or this and this two are giving you the NC signal, and this and this moving contact and this one will give you the NO signal. So how the NO and C will again convert to NC/NO? When the disk will rotate, the spindle also will rotate, and the spindle will comes to here. This is the position of the spindle, or this is the position of the spindle where the relay giving the signal to the circuit breaker. When the spindle will come to here, this will move this moving contact from this terminal to this. That means this moving contact will touch to this one. Then this terminal, which earlier it was NO, it will convert it to LC, and the circuit breaker will detect a fault happen. So we'll see also in details in the next image. But right now our main focus is how to calculate the operating time, or the actual operating time before operating the relay for any particular value of the fault current. So let's analyze for this setting. So here setting is 0.75. So clock setting is 0.75. So if we give let 1.5 ampere of current, then what will be the PSA? So 1.5 divided by 7.75. That means 1.5 is nothing but the fault current upon the clock setting nothing but 0.75 will gives you the PSA, that is 2. So in the scale if you see, if PSA is 2, 10 is retained. That is the calibrated operating time. So what is the actual operating time? We'll see the formula of PSA. I will show you in the next slide. That will be the ratio of actual operating time upon the calibrated operating time. So actual operating time will be multiplication of PSN and this calibrated operating time. So 10 into here 0.7 will give you the 7 seconds as the trip time. That means if we give 1.5 ampere current, we get 7 seconds of trip time. Similarly, if we give 10 times of the 0.75, that means 7.5 ampere of current. If we give 7.5 ampere of current, that means 7.5 divided by 0.75 will give you 10. If we give 10 times of the clock setting, it should trip 3 into 0.7 second of 0.2 times of the trip time. That means if we give 10 times of this current, the trip time will be 3 into 0.7. Similarly, for any value of trip fault current, we can able to calculate the trip time using the scale given. So in our observation, we are also going to do the same thing. We will calculate the fault current or the trip time for a predetermined fault current, and we will compare by operating the relay whether whatever the trip time we have calculated, whether the relay is operating at the time what we have calculated or not. And this scale also will be used when we want to install the relay and we want to protect some test object for a particular value of current. For example, if this relay is used in some particular type of load and the load requirement is trip the circuit if the current is 3 ampere, then correspondingly you have to set the PS and the TSN so that the relay should act at 3 ampere of current or some amount of current at 3 seconds. So that means in reverse way also we can set these two for particular value of current and particular value of trip time. But in our experiment, your particular value of current and trip particular value of current will be given and correspondingly you have to calculate what should be the trip using the setting predefined. Here in our experiment we have to fix the setting of TSM and clock setting and we will get the trip time for a particular value of current. That is we will see in the observation. So, and also I shown you that this is the moving packet and this is giving you the trip signal. Let's see in details. So see the image. This is the disk. This is the disk. This is the breaking magnet, and there is a primary winding and secondary winding is there, upper and lower level in that form. And this is the spindle. This is the rod is attached with the disk, and this knob of the spindle is moving with the disk. When the disk is moving, the spindle is touching this moving terminal, and this is fixed with this one. So this is moving towards the back side of this one and is giving the signal to the circuit breaker, and the terminal is connected like that. And you can see here 1, 2, 3, 4, 5, 10 terminals this relay can have. But right now this relay, this is a picture of the relay which we will test. This is not other picture. This is the picture of the relay we have taken which we will test in our laboratory. So here 1, 2, 3, 4. These 4 terminal is accessible or is there. These are not there. This is the blank terminals. 9, 10 are the available terminals. So we will see the next what are the terminal is connected. And also you can see this is the trip signal indicator of the relay. So now this is indicating the relay is tripped. This is a flap. In normal operating condition, you have to shift this flap to this position by some knob. I will show you when I am talking about XUV. And when the relay will trip, this flap will come down. And by seeing this image, you can tell the relay is tripped. But when the relay is tripped, signal is showing, that doesn't mean that relay will not operate after that. So this only showing the signal, but if this is showing, still also relay can operate. So let's see this one. So this is the unit of the overcurrent relay. This relay is inside this unit, and what are there inside this? Only the terminals from this, and it is accessible over here. To give you easy access of the terminal, this type of unit is made. That means 9, 10, you can see here previously 1, 2, 3, 4, 9, 10 is last two terminal. So you can see this 9, 10 terminal is connected to these two terminal, and this 1, 2, 3, 4 terminal is connected to 3, 4, 1, 2, and this 5, 6, 7, 8 are blank terminals, because here nothing is available. And what are the 9 and 10? 9 and 10, you can see this is the input from the CP. That means this is the current input terminal, that is 9 and 10. And this 1, 2, 3, 4 is the 1, 2 is the alarm terminal, 3, 4 is the trip terminal. Both are same, but one terminal we can use for the alarm, one terminal we can use for the circuit breaker to trip. And that is the NO terminal. That is the NO terminal. Okay. So this all about to study about the relay, and what are the how to use this unit which you are having, and how to test what are the terminals we have studied. Right now I will see about the power supply of the current injection unit. As you can see, let me zoom this one. As you can see here, this is the current injection unit panel. So this panel is having a ammeter, then a time interval meter, then this is the external time accessible points. That means you can use the timer from the externally. Then this terminal we have to use. See the protection timer for the current injection unit. That means you will set this timer for 1, 2, 3 or some point. Then after that time, this circuit breaker will trip the circuit automatically. That is the protection timer for this injection unit only. This current injection unit. And that's why the switch is there. Switch for the bypass and switch for the turning on the timer. Then another auxiliary supply is there. That means wherever the relay is requiring auxiliary supply, from here we have to give. If not required, then this will be left as a vacant. Then there is a terminal for the circuit breaker, or this terminal will be used as the input to this unit or input to the circuit breaker. That means relay output will connect to these terminals. There is NO and NC terminals are there. See NC terminal, that's why you have to short circuit forcefully. So within this one, you have short circuited this terminal, and this NO terminal is left open because this is normally open, and these two terminals from the relay unit will come to these two terminals. So that when the relay will give some trip signal, then this from this the circuit breaker will sense and it will trip the circuit. And let's see, and whatever else is there. So this is the input terminals for the 230 volt power supply. This is the mains, which means this switch is used to turn on the current injection unit. And this is the test start button, this is the test stop button, and this is the trip indication. That means when the unit is giving you the indication of trip, this LED or this indicator will glow. And there is a variac is there. It will vary this one. This can call it as a variac or the auto transformer or the dimmer. So 3 types of names are there. People are using that, but they don't confuse that. So this is the variac. So when we will vary this one, correspondingly we will vary the current output of the current producing unit. So let's see the circuit in details. How the unit is designed, how it can generate the current, that much amount of current, because in the specification section we have seen that this injection unit can generate 50 ampere of current. But you can imagine how in our household we are having maximum to 5 ampere. How 50 ampere is generating? There is some technique we have to use to generate the 50 ampere of current, and that to be from the regular 230 volt power supply. That means our regular home power supply can generate 50 ampere of current. How? We'll see here. So from this circuit diagram, you can see 230 volts coming through a switch is there, then fuse is there. So I can see 230 volt is coming, inside this fuse is there, the switch is there. This is the switch. Then from the output of switch, it is giving the variac distance. Inside of this terminals is connected. Then the output of the variac is connected to the circuit breaker. And as you can see, this symbol showing this is NO. This symbol showing this is NO. And this symbol showing this is NC. Similarly, this. That means as per symbol we have to analyze whether the circuit with the terminal is NO or NC. That means this is NO means this will normally open. When this will be closed, when we will push this start button. So when we push this start button, then this terminal will be closed. Then the output of the variac will be available in these terminals. What is this? This is the key, or this is the main head or important equipment or part of this current injection unit. What is this? This is in other way this is named as current injector. But what is the real? What is this unit? This unit is nothing but the current transformer. This is nothing but the current transformer. Or what it does, it converts voltage into current. That means it will give a small voltage and correspondingly it will convert into current. That means here maximum voltage you can give 30 volt, it can generate maximum current 50 ampere. But from the input side or from this side it will take maximum 5 ampere. That means the whatever 5 ampere is converted to 50 ampere. Then what is there? The output of this current injector is connected to a switch S2. What is the S2? We'll see S2. So you can see this is the unit, and in the left side of this unit we are having two switches. So this switch is nothing but S2. This switch is nothing but S2. So it is having position of 1 and 2 in two position is there, and it also written current output 1 for current, 2 for this open. That means what? If the position will be 1, the current will be there. That means through this switch current will be there. So what will happen? Through the switch current is there means there is no current on this two terminal. This current is bypassed through this. So S2 is there to decide whether current will be available on this two terminal or not. If at position 1 current will not be there, at position 2 current will available here. At position 2 the DC will be open, so current will be available here. And also you can see ammeter is connected. And in which way ammeter is connected? This is connected through a CT, not directly through this one, because this relay can measure maximum this current injection unit can give maximum 50 ampere current. So as you can see, if you will give maximum 50 ampere current, only with a 1 ammeter you will measure, what will happen? That 50 ampere current we have to measure with this one, and as well as 1 ampere current also happens through this one. So no such ammeter is there which can give a higher accurate value of 1 ampere as well as 50 ampere at the same time. So that's why CT is there. So our maximum scale or the full scale reading of this ammeter is 1 ampere. That's why through a CT it is connected, it is adjusting the ratio. Whatever the current will feed, it will convert into 1 ampere scale. We'll just see here 1 ampere according to the CT ratio, original current will be flown. So where CT ratio are adjusting, as you can see in the left, which is there current range heads up. So here this range selection switch is adjusting the safety ratio of this ammeter. So what happens at position 1 it is getting 1 ampere, position 2 2 ampere, position 3 5 ampere, position 4 10 ampere, like that. So if we want to give 3 ampere of current, so what we have to do, we have to select position 3 in which you can give maximum to 5 ampere, and you have to see here 3 by 5. That means when we increase this area, here you will see 3 by 5 at position 3, that will corresponds to 3 ampere of current. So 3 by 5, what will be the 3 by 5? That will be 0.3. So whatever, 3 by 5. So, and another switch is there, that is a stage stop order. That means when the signal will come to this NO and C of the circuit breaker of the current injection unit, then this circuit breaker will trip the circuit and it will give a signal of trip by indicating this one, and also it will indicate here also, that means it is trip, and to operate again we have to reset it. So we have to place this test reset order or test stop order, and this switch also will be. So we'll see in the procedure how to operate this one, that will see step by step, but you can see that this function of this switch is to allow current to the relay or not allow to the relay. This switch will decide, and this switch will decide how much current we can apply to this current injection unit. If injection unit is 1, position 1, then this unit is maximum can supply 1 ampere, position 2 2 ampere, position 3 this can supply 5 ampere. Similarly position 6 is 50 ampere. That means it can supply 50 ampere. That is the full scale or the full output capacity of the current injection unit. So this is studied. Next we will see. So as you can see, this is the diagram details as we have already started in this one. So now we have to look at this. So next is the connection diagram. So we will go to the experiment table and we will show you the connection and then the rest of it. Right now we are in the experiment table and we will see how the equipment is connected. So from this image you can see that these two terminals, that is the current output of the current injection unit, will be connected to the current input, that is 9 and 10, as already I have said, 9 and 10 of the electromechanical relay, and the output that may be 3 4, may be 1 2, because both are common, one for the alarm, one for the trip time. So that will come to the NO terminal, as you can see, NO terminal of the relay, sorry, in current injection unit. And now we are in the experiment table. Here this one is the electromechanical relay unit, this one is the current injection unit. From here to here we have to connect. So from here current is going to terminal number 9, from here current is going to terminal number 10. Similarly trip signal will come from terminal number 2 and 1 to the NO terminal of the current injection unit. This is about the connection. Now we will see what are the settings required to perform the experiment. So before that we have to see the procedure, but you can see there is some precaution we have to perform. We have to see what should be precaution. That's a common precaution, but main technical precaution is relay settings should not be changed. That's the general. Next, this is the procedure. So as you can see, if you follow the procedure step by step, what should we do? I already explained the current injection unit, each part, each button. So we will see step by step. So your first step is, your first step is connect the circuit as per the circuit diagram. So already we have connected the circuit as per the circuit diagram. Then ensure time interval meter switch in T position. So as you can see here, this is the protection timer and this is the timer switch.
this will be in bypass mode. Sorry, this is the external time interval team position. This should be in external or team, that depends on the process. The process is should be in team position. So this is in team position. Next is bypass the timer switch. Ensure the protection timer switch is bypassed. So as you can see here, protection timer is bypassed. Off side is bypassed and the bottom side is turned on. So it is bypassed. Then bring dimmer to 0. Bring dimmer to 0. As you can see, this is the dimmer. This is the dimmer, or in other way you can call it a auto transformer, or in other way you can call it a variac. So anything you can call. So right now it will rotate in anti-clockwise direction like this. Then it will come to 0. So we have to make it 0 means we have to rotate fully towards the anti-clockwise direction. Now it's not rotating, so that means being dimmer is 0. Now next process you will see, put the mains using mains on rocker switch. As you can see here, there is a rocker switch, mains on rocker switch. This we have to turn it on. Power supply is not connected, so that's why it is not able to turn on. So this is the mains rocker switch. Next, select the current using current selection switch. So right now select the current that you will see when you will see the observation table. How will select the current? That depends on how much current we are going to apply. Next, bring rotary switch position 1 for not allowing current to the relay. As I said, there is another switch is there. This switch, that is the rotary switch. That position we have to fix it to 1 so that the relay current will not pass to the relay, as I said earlier. Now push test start button. So this is the test start button. Here you can see, this is the test start button. You have to push. Then adjust the dimmer position for a particular fault current. Adjust the dimmer position for a particular fault current. So right after that we will adjust this one for a particular value of fault current, and we will note down the fault current from the ammeter reading here. Then bring rotary switch position to 2. There another switch is 2. Rotary position 2 we have to make it to 2 so that the current will suddenly go into the relay and the relay will give the trip signal. And next step is note down the fault current. That means once the relay will give the trip signal to this circuit breaker, then the timer will stop and it will tell you what is the trip time. The timer will start when the position of the rotary switch at position number 2. So position number 2 means current gone to the relay, and when the relay will give signal back to the circuit breaker, then the circuit breaker will, when circuit breaker will trip, then the timer will stop and it will tell the time of the trip. Then we have to note down. Then press reset button. So this is the whole process right from the start to stop. And then you have to repeat for next observations. Like we have to take 10 observations. So out of 10, we have to plot the graph using this 10 observations. Next, switch up the power supply, draw the time process graph. This is the procedure we have to follow. Now, this is the observation table which we are going to see. So, as I told you, in our experiment, clock setting and TSM is constant. You have to fix for some value. So, right now, we have fixed it to 0.6. Fixed it to 0.6. And clock setting, we have fixed it to 0.75. So these are fixed settings. You have to fix inside the relay. These are the relay settings. Then fault current. This is already predefined the current we have selected. You can select any value of current. And here 0.75 we have selected as a fault current. So that means clock setting. So that means fault current should be more than 0.75. That's why 1 ampere we have taken as a fault current. More than 1 ampere we are taking, and that means fault current is increasing. So as I said also, PSM also you can able to calculate that PSM will be fault current divided by clock setting. So this will be 1.33, like that we already divided and we have written here. And also I have shown you how to calculate the trip time without operating the relay or before operating the relay using for a particular value of fault current and for fixed amount of TSM and clock setting. So here, let example I will see. Let 3 is there, 3 ampere of current, or let's say 1.5 ampere of current. So here 1.5 ampere current that is fixed we have to give, and 0.75 is the clock setting. Correspondingly you are getting 2 ampere as the PSM. So if you are getting 2 ampere as the PSM, then corresponding to, as I shown you earlier, that corresponding to, if you look at the image, let me show you. If you look at the image corresponding to 2, as you can see, corresponding to 2, here corresponding to 2, there is 10 is there. So 10 is means that is the calibrated operating time. 10 means that is the calibrated operating time, and you can see for corresponding to 10 is the how we will calculate the actual operating time using this, using the TSM. So that 10 into 0.6, 10 into 0.6 will become 6 seconds. So this we have calculated without operating the relay. Now we will operate the relay, and we will, before that we will set the PSM and PS and TSM, PS and TSM, and we will operate the relay, and we will see whatever the time we have predicted or calculated from the scale of the relay, whether that time is coming or not. We will compare. In this way also we compare, and also we will see the characteristic or the trip time is less if we will increase the current or not. As you can see here, this trip time is reducing when we are increasing the fault current. So now we will take the observation. So as per our observation, we have to set 0.75 for the clock setting and TSM 0.6. Here as you can see, it is set for 1.25, but we will set it right now to 0.75, and similarly here you can see it is 0.7. We will change it to 0.6. So how to change? Let's see. First we have to remove the plug like this. Then here this is a plug setting, because why it named as plug setting, because this is only a plug. Like our 5 ampere 6 ampere plug we are using in our home, this is like a plug, only a plug. So we have to insert into 0.75. So it is now 0.75. Plug setting is right now 0.7. Right now we will change this to 0.6. So how we will change? You can see we have to remove very smoothly. We have to remove to 0.6. Right now it is set to 0.6. So here, as I told you earlier, this is a flap. This is a flap. This is the trip signal indicator of the relay. Right now it is showing relay is tripped, but without this, when the this indicator showing trip, at the same time relay can able to operate. But this is only an indication for any user that relay is tripped or not. So how to reset? So there is a this part is there. We have to push it like this. So the now relay is resetted. Only to, this is an alarm type of signal. Without this also relay can work. And next, as I told earlier, how much current we will apply in our observation table. Our current will start from 1 and maximum it will go to 5 ampere. So that means which current selection switch you have to use. As I shown you, this ammeter cannot measure directly the current which is flowing to the relay. It will measure through the CT. You have to adjust the CT ratio. This alternatively known as current range selector. As you can see, current range selector, this is the switch. Here for one position 1 ampere, 2 ampere, 3 5 ampere. So we have to select for 3, because it is maximum we can give up to 5 ampere, and we will start from 1 and we will end at 5 ampere. So in that way we have to apply. So this, and also this switch initially should be 1%, as already told you. So this is the settings we have to do before doing the experiment as per our observation table. So let's turn on the equipment. Now we have turned on the apparatus, and right now we will perform the experiment as per our observation. If we will see that we have to apply 1 to 5 ampere of current as a fault current, but instead you can see up to 1 to 1.75 we can choose current selection switch position 2, because at position 2 we can go up to 2 ampere. Similarly at position 3 we can go up to 5 ampere. So that's why After 2.2 to 5, we have to select current selection switch position to be position number 3. So right now, as you can see here, the position of the current selection switch we have selected to 2. So with the position of current selection switch to give 1 ampere of current, as you can see, to give 1 ampere of current, how much you have to see? 1 by 2, 0.5. 0.5, you have to see 0.5 here. So before that, this should be 0 and this switch position should be 1, and we have to press start button. So we have pressed the start button. Now we'll increase this and up to 0.5. We'll increase this up to 0.5. 0.528, 519. As you can see, 0.51 it is there, and it is we are ready to fire the 1 ampere current to the relay. So the relay disk is moving, and at the same time timer is running. So when the relay will give its signal to this unit will trip the circuit as well as it will stop the timer. So timer stopped. We observe time as 13.78. So not much difference. Next we will go for 1.2 ampere of current. That will be 0.6. We have to see here. We have to see 0.6. So again make to 0, and the switch position put it to 1. Then the tap reset. Then we have to see for the 0.6. 0.6. And we'll apply the current again. So we will see here how much the relay is giving the trip time, 8.4 seconds, and here we have calculated 9 seconds. Next, reset this to be 1, and next for 1.5 we have to see 1.5 by 2.75. So we have to see 0.75 because that is 0. 0.75. So 0.75. Now I will apply the current, changing the S2 position. Now our expected time is 6 seconds. We got 5.8 seconds. So it is nearly equal. 5.8 seconds. Similarly, reset this to be here, and again this to be 0, and this to be here. Then we have to give for 1.7. 1.7 signifies how much? 1.7 by 2. It will be, this is 0.75. 1.7 by 2, it will be 1.7 by 2 is 0.85. So we have to see 0.85 here. So okay, start this one. Already started. We will increase to 0.85. As you can see, you have to see 0.85 here. You have to see 0.85 here. Now you will see the time. Our expected time for this current is 4.8 seconds, and we got 4.9 seconds. So exactly similar. Next stage, we have to apply 2.2. For that, we have to change the position to position number 3. We have to change the position to position number 3 for the current selection switch. So here this is the position we have changed. Here we have changed to position number 3. So in position number 3 for 2.2, how much we have to see? 2.2 divided by 5. We have to see 0.44 here. 0.44 here. So next at question number 3, this should be question 1, tap reset, then this should be 0, then again start. How much we have to see? That will be 0.44. So 0.44, 0.47, 0.46, 0.45, 0.44. Let me 0.44, 0.448. As you can see, we are seeing at 0.448. So we give the current to the unit, and our expected free time is 4.2 seconds, and we observed as 4.4. Now our next observation is for 2.5. So that means we have to see 0.5 here. We have to see 0.5 here. So this will be 0, that we have to see 0.5. As you can see, 0.5. We observed here 0.5. Now we will give this one. When we are changing that rotor switch, as we already told, that relay will detect the current. Unit will transfer the current to the relay. So time is 3.9 seconds. Our expected is 3.6 seconds. 3.9 seconds. Now we will give for 3. So if for 3, how much we have to see? 3 by 5, that will be 0.6. Here we have to see 0.6. So position to be clear. This should be like this, and this should be 0. Then press start button. Then open this to 0.6. We have to increase to 0.6. Okay, this is 0.6. So after that we have to see what is the flip time. We have expected 3 seconds, and it is 3.2 seconds. Now for 3.5 we just have to see 3.5 divided by 5 is 0.7. Right now you will see 0.7. To reset, again 0, press start. We have to give for the 0.7. And we have to turn on. So after that 3 seconds, 3.0 seconds, we have observed 2.8 seconds. Now for 4 by 5, this is 0.8. So we have to give for the 0.8. 1, reset, then space this will be 0, press start, and we have to equal to 0.8. So as you can see, we have applied 0.8. So right now this signifies to 4 ampere. Now we will give the supply to the relay. So it gave 2.6 second, and last is 5 ampere. So 5 ampere we have to reset. You have to make it 1. As you can see here, this there is a lower one, upper one, any one, in this way one or in this way one, any one we can do. So this one, and we have to give for the 5 ampere. That means we have to see 5 by 5, 1 ampere here. How much? 5 by 5, 1 ampere. So turning on, we have to increase this one, increase this to 1 ampere. As you can see, 0.98 8 1. This is 1. As you can see, this is 1. This is 1. So 1 signifies to our 5 ampere of current. Let me tell you now. So how much trip time? 2.3, and our expectation is 2.28. So in this way we have observed 10 observations, and also in the observations we can see that whatever the time we have calculated from the scale, it is nearly similar to the or nearly equal to the actual trip time or the actual trip time of the relay. So and also we can observe that this current or this trip time is reducing when we are increasing the current. Current is increasing, this is reducing, that means this is the identity or the inverse characteristic. So then what we have to do after this? After this we have to plot this observation in a table. Then after that we have to plot the graph between PSM with respect to trip time. Then we will observe that it will be an inverse characteristic. And one question you may be asking after drawing the graph, that why we are drawing the graph between clock setting multiplier versus trip time? Why not we are drawing the graph between fault current versus trip time? That is because as already in the first section or in the theory section of the relay, I have told you that at any value of clock setting, here this is the relay clock setting. So at any value of clock setting, the relay characteristic is identical. So right now clock setting is 0.75. So at 0.75 your clock setting will be whatever type, it will change that to 1 also, that characteristic also will be same profile. Means the inverse characteristic or inverse profile is same. So that's why we have to fix only one case and one PSM, and we have to plot a graph. So this is the experiment of electromechanical overcurrent relay, and in the next part we will study the numerical overcurrent relay.